Okay, so welcome again to another video lecture series for integral calculus. Okay, so we are still on the chapter on techniques of integration. So for today's discussion, we will be having algebraic substitution. Okay, so for today's topic or for this topic, we will be using a few of the common formulas for the integrals. We have the form or the power formula. You have integral of u raised to n du. We know that whenever we encounter this form or the power formula, the resulting integral results into the form u raised to n plus 1 over n plus 1 then plus c. Okay, so next is the integral of the form of the logarithmic base e raised to u du. This results into e raised to u then plus c. Finally, we have the integral of du over u as equal to the result of the integral of du over u is ln of u then plus c. Okay, so for algebraic substitution, this is actually a common technique that were presented early on in our solutions to integrals or the antiderivative, but we haven't fully emphasized the some of several cases of applications of or techniques for this algebraic substitution. If you remember, in the previous topics, we usually make use of a technique that we let u equal to an expression in our integrand. Okay, so this is basically what we do in algebraic substitution. Okay, so let's take on a few examples. So let's have example number 1. We have integral of x over x plus 1 square dx. Okay, so for this, we usually let u equal to the more complicated part of the integrand. So between the numerator and the denominator, of course, x plus 1 square has the greater complexity as compared to simply having let u equal to x. So instead of having let u equal to the numerator, we make use of the let u equal to the term in the denominator, since the denominator is more complex as compared to the numerator. So okay, so let's proceed. Let us let u equal to x plus 1. And of course, if we're going to solve for for x, we simply transpose positive 1 to the other side, to the side of u. So that becomes negative 1. So this becomes x is equal to u minus 1. And of course, du is equal to dx. Now take note, why do we need to solve for x, or why do we need to represent x in terms of u? Try to notice if you're going to have this as u square, of course we need to express the remaining part of the integrand in terms of u, since we represent already the denominator in terms of u. Now, so this means if we're going to let x plus 1 equal to u, this becomes u square, and we have a representation of dx in terms of du, so we replace dx with du, but we will be leaving out x that has no substitution. So therefore, we need to express, or we need to find an expression that we can replace x in terms of u. So this means we need to solve, since we represent u equal to x plus 1 and we can solve for x from here, we can actually make a replacement of x in terms of u as x is equal to u minus 1. And of course, all of these terms, all of these substitutions are in terms of algebraic expression. Thus, the name algebraic substitution. Okay, so let's proceed with the actual substitution. Okay, so our original integrand becomes u square, x becomes u minus 1. Of course, dx becomes du. Now, simplifying further, if we're going to separate our fractions, a fraction into two fractions, you have u over u square minus 1 over u square. Of course, u over u square becomes 1 over u, or simply du over u, minus, of course, u raised to 2 can be written as u raised to negative 2, so that we can apply the power formula here, and we can apply ln of u here. Now, so performing the integration, so we have integral of du over u becomes ln of u minus, of course, this for the second part of the integral, we make use of the power formula, so that becomes negative u raised to negative 2 plus 1 over negative 2 plus 1. So this becomes this becomes u raised to negative 1 over negative 1. Of course, negative negative becomes positive. So this becomes ln of u plus u raised to negative 1 is the same as 1 over u, then plus c. Now, replacing back the value, the representation for u in terms of x, we have u as x plus 1 over 1 over x plus 1. So therefore, our original integrand becomes integral of x over x plus 1 square. Dx becomes ln of x plus 1 plus 1 over x plus 1, then plus c. Okay, what is complex with this topic, algebraic substitution, is that it is not always apparent the portion of the integrand that is that we're going to represent in terms of u. So at this point, what we actually need is a sort of mathematical maturity in order to decipher somehow how would we able to which part of the integrand would we decide to represent in terms of u, and which part of the integrand would be represent in terms of our algebraic substitution. Okay, so let me repeat that. What is required up to this point is a sort of mathematical maturity, since we are actually dealing with higher mathematics. I know that it would be quite difficult at your end, but of course you are. This is what is required in this subject. This subject requires higher. This subject is actually higher mathematics, so it requires some sort of level of mathematical maturity. Okay, so but at the moment, let us perhaps we could content ourselves with choosing which part of the integrand to represent as our u, in terms of which part of the integrand has more complexity in terms of the other parts. So at the moment, let us be contented with that, and let us try to make use of that in terms of other examples. Okay, so let's apply that in the example number 2. So here we have integral of x square root of x squared minus 1. Obviously, between the terms x and square root of x squared minus 1, square root of x squared minus 1 is the more complex of the two terms. So if we're going to represent u as equal to x squared minus 1, then solve for the representation of x, since obviously we cannot leave out any x in our substitution that we will not be representing in terms of u or du. Okay, so let me repeat that. The idea for algebraic substitution is that if we're going to let u equal to an expression in terms x in terms of u, there should be no x's that will not be represented in terms of u. So therefore, it's a total conversion of all the symbols of x in terms of u. Try to notice this transition. This is the original given. Notice that every excess here has been represented in terms of u. So therefore, one of your guide in order to successfully make an algebraic substitution is that all of the symbols for x has been represented in terms of u. Okay, so just like what we see here. Okay, so knowing that, now we let u equal to x squared minus 1, and solving for du becomes 2x dx. Of course, this is 2x dx. If we're going to solve, this means that we should be able to represent x squared minus 1 square root in terms of u raised to square root of u. We could replace dx in terms of du over 2 is equal to x dx, but we will be leaving out x. So therefore, we need to find a representation for x here. But notice, since we already solved for du as 2x dx, we can actually solve for x dx as du over 2. So that means we just need to rearrange our original integrand to form x dx. So therefore, doing that, we have integral of x square root of x squared minus 1 dx, in rearranging the terms as x squared minus 1 raised to 1 half and x dx. x dx is represented as du over 2, and of course x squared minus 1 is u raised to 1 half. Okay, so of course, at this point, this is a common form of the integrand. We just bring out the constant outside the integral sign. So we have 1 half integral of u raised to 1 half du. We just apply the power formula here, then we can solve the integral. Okay, so that becomes u raised to 1 half plus 1 over 1 half plus 1. That becomes u raised to 3 halves, 3 halves, over 3 halves. Of course, 1 half and 3 halves is you cancel over 2. That becomes 1/3 u raised to 3 halves then plus c. Making the substitution for u, this becomes x squared minus 1 raised to 3 halves times 1/3 then plus c. Okay. Okay, so let's have example number 3. We have integral of e raised to 2x over 1 plus e raised to 2x dx. Obviously, between the numerator and the denominator, you have the denominator as the more complex of the two. But if we're going to represent it with try to notice, if you're going to represent the whole denominator as u equal to 1 plus e raised to x, that means you still need to represent your e raised to x in terms of another substitution. So try to do it. Try to explore the answer, an alternative solution. If you're going to represent u equal to the whole of the denominator, meaning 1 plus e raised to 2x, and try to see if the solution for representing the whole denominator in terms of u be equal to the solution presented here. The difference in the presentation in the solution here is that only the portion of e raised to 2 raised to x is represented as u, not the whole denominator. Okay, so I hope you get that. Try to explore if you're going to arrive with the same answer. Okay, so but for this portion of the solution, we left u equal to simply e raised to 2 raised to x, e raised to 2x. Of course, if we're going to compute for du, remember your derivative for the form e raised to u. Derivative of e raised to u is e raised to u derivative of u. So this means this becomes e raised to 2x. This becomes e raised to 2x times the derivative of 2x, which is 2 dx. So that is why you have du here as equal to 2 e raised to 2x dx. Now, of course, if we're going to solve for e raised to 2x, which is our numerator, e raised to 2x dx, that would be du over 2. So this means we simply rearrange our integrand in the form of e raised to 2x dx over 1 plus e raised to 2x. Of course, e raised to 2x dx is our du over 2. Our denominator becomes 1 plus u. 1 half here is a constant, so we can place that outside the integral sign. So that would be 1 half integral of du over 1 plus u. Now, of course, at this point, we need to realize that in order to perform the integral, we need to represent again 1 plus u in terms of v. Any other letter would do, but at this point, at this solution, I have used v for the representation. Okay, so v is equal to 1 plus u is equal to d, and dv is equal to du. Now, our point in the solution, 1 half integral of du over 1 plus u, becomes 1 half integral of dv over v. Now, notice, of course, the integral of dv over v results into ln v. So this means you have 1 half ln v then plus c, making our replacement for v, that becomes 1 half ln of 1 plus u, and making our representation for u as e raised to 2x. This becomes 1 half ln of 1 plus e raised to 2x then plus c. Notice that I have made use of the representation of let u or let v, or meaning this I have done this representation twice in the solution. Now try to explore if you're going to represent instead of simply e raised to 2x as our u, try to explore if you're going to arrive with the same formula, or if the same solution, if you're going to let u equal to the whole of the denominator. So instead of simply let u equal to e raised to 2x, perhaps you could start with the solution with letting u equal to 1 plus e raised to 2x. Okay? So try to explore if you're going to have the same answer for the solution. Okay, so let's have example number 4. Okay, so let's have integral of x over square root of 2x minus 1 dx. You need to integrate this definite integral from 1 to 5. Okay, so at this point we let u equal to the whole of the square root of 2x minus 1. Okay, so of course we have x dx. We need to find a representation for dx. We need to find a representation for x. Now, so from here, if you're going to if you're going to solve for x, simply this becomes first u squared is equal to 2x minus 1. From here we solve for x. X becomes u squared plus 1 over 2. So we can replace x with u squared plus 1 over 2. Also, we need to find a representation for dx. Dx becomes, if we're going to find the derivative for this expression, this becomes 2u du is equal to 2 dx. We solve for dx, that becomes u du. Okay, so doing the replacement, our x is this one here. So that is u squared plus 1 over 2. U squared plus 1 over 2 is our x. Our dx is u du, so that is u du, and the square root of 2x minus 1 is our u, so that is u here, u there. Okay, so notice that we have a 1/2 here. We could place that outside the integral. So what is left here is u squared plus 1. Of course, also we have u over u. We could cancel this u, so what is left there is simply du. So therefore, we have u squared plus 1 du, which is, of course, we need to distribute the integral sign and the 1/2 and du to both u squared and 1. So that becomes integral of u squared du plus integral of u. That becomes u cubed over 3 plus u. We need to evaluate the results from 1 to 5. So replacing u with the original representation for u, which is square root of 2x minus 1, this becomes square root of 2x minus 1 raised to 3 times 1/3 u, or divided by 3, plus square root of 2x minus 1. At this point, we will be doing the substitution of the upper maxima and the lower minima in our result. So the first term here is the substitution of the upper maxima, which is 5, minus the substitution of the lower minima in the same expression. Okay, so notice you have here 2 times 5 gives you 10. 10 minus 1 gives you 9. Square root of 9 gives you 3. 3 cubed gives you 27. 27 divided by 3 gives you 9. So that is the 9 that appears here. Okay, next you have 2 times 5 gives you 10. 10 minus 1 gives you 9. Square root of 9 gives you 3. So that is the 3 that appears here. Now, of course, 9 plus 3 gives you 12. 12 times 1/2, or 12 divided by 2, 2 gives you 6. So that is the 6 that appears here. Okay, so next, we have 2 times 1 gives you 1. 1 minus 1 gives you 0. So this means this is simply this is simply 0. Okay, so plus this is also 2 times 1. That gives you 2 minus 1 gives you okay, so let me repeat that. Let me repeat that again. This is 2 times 1 gives you 2. 2 minus 1 gives you 1. Okay, so square root of 1 is 1. 1 cubed is also 1. 1 times 1/3 gives you 1/3. Also, you have plus 2 times 1 gives you 2, 2 minus 1 gives you 1, square root of 1 gives you 1. So this means you have, you actually have 1/3 then plus 1. So that is 1/3 plus 1. That gives you 4/3 times 1/2 outside. So that means you will be canceling 4 and 2. You will be left with 2 in the numerator. So that means you will have negative 2 over 3. So that is what appears here as minus 2 over 3. So finally, you have 6 minus 2/3. Of course, 3 times 6 gives you 18 minus 2 over 3. 18 minus 2 gives you 16 over 3. Okay, so the final result would be 16 over 3. Okay, so try to do a replay of the video if you got lost in the solution here, in the substitution. Okay, so last example, we have example number 5. You have integral of x squared, square root of 1 minus x dx. Okay, so at this point, we let u equal to square root of 1 minus x. Of course, u squared becomes 1 minus x. Solving for x, x becomes 1 minus u squared. And of course, dx is negative 2u du. Okay, so doing the substitution, you have x squared as, since x is 1 minus u squared, your x squared becomes 1 minus u squared square. This is your x squared. Next is square root of 1 minus x becomes your u, so that is the u here. And finally, you have dx as negative 2u du. Okay, so that is this is your dx, this is your x, and this is your x squared. Okay, so we are left with this form of the integrand. Notice that we have negative 2 here. This is a constant, so we can place that outside the integral. So this becomes 1 minus u squared square. Of course, we have u times u. U times u becomes u squared du. Now, notice that we can expand this binomial. This is a binomial square. So that becomes, if we're going to expand that binomial, this becomes 1 minus 2u squared plus u raised to 4. Then you also have u squared outside the grouping. We could also distribute that to the 3 resulting terms. So this becomes u squared minus 2u raised to 4 plus u raised to 6. Now at this point, we can distribute the integral, the negative 2 and du, to each of the 3 terms in our resulting algebraic expression. So this becomes negative 2u squared integral of u squared du. Negative 2 times negative 2 becomes positive 4. U raised to 4 du. Negative 2 times u raised to 6. That is negative 2 integral of u raised to 6 du. Okay, so at this point, we make use of the power formula. So this becomes u raised to 3 over 3 times negative 2. That becomes negative 2/3 u raised to 3. U raised to 4 becomes u raised to 4 plus, u raised to 5 over 5. This becomes 4 over 5 u raised to 5. U raised to 7 over 7. This becomes negative 2 over 7 u raised to 7. Okay, so at this point, we do the substitution, the replacement of u. Okay, so u is our square root of 1 minus x. Okay, at this point, we do the substitution of the upper maxima minus the lower minima. Okay, so notice that if we're going to replace x with 1, what results here is 1 minus 1 becomes 0. So everything here in each of these terms becomes 0. So that is why the resulting substitution of the upper maxima becomes 0. Then minus the substitution of 0 or the lower minima in the expression. So this becomes 0. 1 minus 0 becomes 1. Of course, square root of 1 cube becomes 1. So essentially this becomes 1. This becomes 1. This also becomes 1. So what is left in the whole expression is negative 2/3, positive 4 over 5, and negative 2 over 7. Of course, this is a simple addition of fraction. This should result into positive 16 over 105. I'll just leave you the solution of how did we able to get 16 over 105. Okay. Okay, so this ends our discussion on algebraic substitution, and I'll be asking you to do the algebraic substitution or the solution for the following exercises.